The first presentation, I'd like Lanier Watkins, Dr. Lanier Watkins, to come up. He's going to be talking about assuring autonomous airspace. He's from APL. His co-PI is Louis Whitcomb, who could not be here today. He's from the Department of Mechanical Engineering. So, Louis, I'm sorry, Lanier.
All right, let me get this. Oh, I'm going the wrong way. All right, so as David said, I'm Lanier Watkins, and on behalf of myself and Louis Whitcomb, I'm here to present the summary of the work that we did for years 1 and 2. My presentation is entitled Assuring Autonomous Airspace Operations. And here is a picture of my project team. Just want to give an acknowledgement to them. And so I have about 20 slides, so I'm going to really do my best to keep this within 10 minutes, so just bear with me. So I'll start by saying that the aerial landscape is changing. There are several vendors that right now you can take part in them offering drone services, and this is expected to boom. As a matter of fact, it is predicted that by 2035, in the airspace below 400 feet, that there will be a boom in drone operations on the order of 65,000 operations per hour. Just to give you an idea, the business airports handle less than 300. And so FAA is handling this using what's called UAS traffic management, or UTM. It's a conceptual framework of complex interactions between operators, customers, and a UTM system. Essentially, it allows for customers to provide flight plans. The system would deconflict these flight plans, and then the drones would take off and perform their services, and they have some sort of collision avoidance on board. The only issue is that there are a lot of man-in-the-loop operations within this. So if we're to achieve this expected growth, then we're going to have to embrace autonomy. So to study this problem, our approach was to build a simulation tool. And in year 1, this simulation tool was really in 2 dimensions, used perfect sensors, and in year 2, we moved to 3 dimensions and noisy sensors. And we also built some methods to assure the autonomy. So in year 1, and this is work that was published at the IAA conference, essentially we evaluated a portion of the UTM ConOps using a set of autonomous algorithms for flight plan deconfliction. Specifically, as I mentioned before, strategic deconfliction is essentially taking those flight plans and ensuring that there are no overlaps. It was done using temporal. So in other words, the drones were staggered such that if they flew those static flight plans, they would not collide. And also each drone had on board a collision avoidance system to take into account for collisions with any dynamically moving objects. So strategic and tactical deconfliction provides safety in congested airspace. And this is an experiment that sort of speaks to that. Even when the majority of these drones have completely deviated from their conformed flight plans. And so we also looked at how would you ensure that the autonomy algorithms that we're using for strategic deconfliction actually doing what they're supposed to be doing. So we looked at building a fuzzy inference system. And essentially this fuzzy inference system polices these thresholds, closer warning and further warning. And so if there are any obstacles that breach those warnings, those thresholds, then that would increase the risk, the airspace risk. And this is essentially a way of looking at the decisions that are being made by the autonomous UTM system to determine if they're actually increasing or decreasing airspace safety. And so this fuzzy inference system also allows us to be able to explain the decisions that are made by looking at the FIRE rules from the fuzzy system. And as an example here, the fuzzy rules that are in the boxes there, these are the ones that actually corresponds to the two situations we have here. Essentially, for high risk, this is a scenario where there is no strategic deconfliction. And the rule that FIRE is number 4 there, and as you can see, that essentially this is a scenario where there were heavy collisions or heavy breaches in that closer warning threshold. And also, I think has a mind of its own. Also, for lower risk, the rules that are applicable are number 5 and 6. And so you would think that schedules decrease the amount of UAS close encounters. And as you look at the rules there, for closer warning, you have light close collisions. So you have hardly any UAS breaching this particular threshold, and thus you have low risk reported. And this confirms that the behavior that we are expecting from the algorithm actually exists. And then in year 2, we looked at more realistic airspace or more realistic scenarios where you have a 3D airspace and noisy systems. And also we looked at assuring the tactical deconfliction algorithms. And this is work that we're submitting to flagship IEEE journal. So in year 2, we investigate airspace safety in more realistic scenarios. And as I mentioned before, 3D airspace, noisy signals, flight plan uncertainty. And these are some of the experiments. These are results from the experiments that we run. And here, as I mentioned before, the detect and avoid or collision avoidance algorithm its assurance confirms that the behavior it confirms that the behavior of the collision avoidance algorithm is as what we expected. It also complements the work that we did in year 1, where we looked at assuring the strategic deconfliction. And again, this is assuring that second piece. This is the part where the collision avoidance algorithm is on each drone. And the way this works, essentially there's only one threshold around the drone. It also looks at its next waypoint, the distance to the next waypoint, and then it also looks at the time it takes to get there. So there will be an increase in airspace risk if the algorithm essentially did collision avoidance and made widespread deviations from the waypoints, from the confirmed waypoints. And so also in year 2, we were able to extend the autonomous UTM, the notion of an autonomous UTM to a new domain, search and rescue. And so by using this autonomous UTM system, we are able to create something that may seem paradoxical, but this notion of a hasty grid search and rescue. With hasty search and rescue, you essentially use a minimum number of resources, and you're only looking at the areas in which a target frequents to try to quickly find them. With the grid research, with the grid search and rescue, you essentially want to do a very thorough search with the maximum number of resources you want to overturn every corner. But using this notion of an autonomous UTM and also allowing these UAS to be coordinated in terms of their missions, we could actually sort of do both. So the autonomous UTM system allows you to basically stack airspace with as many drones as you could possibly need to be able to search every single portion of the area below. And again, UTM provides safety. Here are some of the experiments that we did. And this work was done in conjunction with my colleague or my collaborator at the United States Air Force Academy. He actually came down for a week, and he helped us sort of put this into hardware. So hopefully I can keep going and we can get to the really cool stuff, experiments that we did at the APL farm. So some of the experiments that we did, we noted that wind turbulence doesn't really affect this search and rescue because we're doing essentially a SAW pattern for search and rescue, and the wind turbulence doesn't really affect that much. However, visibility does affect the ability of the search and rescue, the performance. So in other words, if you have high obstacle density, if you have very rough terrain, or if the sensors themselves have very low visibility, then the performance is affected. And these experiments help us understand or sort of give us evidence that the UTM system itself does add value. Again, it allows you to safely pack the airspace above the area that you want to search and ensures that there are no collisions. And so we did some summary experiments, and we came up with this sort of quick summary that considering an area of about 9.6 square kilometers, for UAV with about 20 minutes of battery time could find 15 targets in this area. So here's an example. Let me try to, looks like the video won't play, but essentially this is a video here that sort of shows the search patterns. So here's a really cool stuff here. Like I said before, experiments that we did at the APL farm. We first tried this out in my office using ArduPilot. We used a MATLAB simulator. It simulates a UTM environment, provides these waypoints, and then ArduPilot sort of enacts this in real life. And we actually went out to the farm and did these experiments. You can see drone takes off, drone does a zigzag pattern. We have a human target out there. Drone is able to see the target and then return home. And here's a list of the publications and patent disclosures that we did with the work. I don't know if we're allowed for questions, but if you have any questions, you can send me an email. Oh, any questions?
Lanier, I'm curious about the funding situation for the low altitude air traffic control. Is this something that the FAA is still interested in? I've heard different stories. I would have bet that it's even more interested over time.
Yes, FAA actually did fund my group, small amount of money to do some additional work. It sort of deviates a little bit because that conceptual framework of UTM that I sort of mentioned, they are deviating slightly from that. So some of the experiments are a little bit different. Like for instance, they want to know, is both strategic and tactical deconfliction absolutely necessary? What happens if one of them goes away? So again, we were funded to do some of those very nuanced scenarios. And I'm hoping that if that work goes well, then it'll be larger funding on the tails of that money. Any other questions? Thank you for your time.
Okay, so next, thank you very much, Lanier. That was really interesting. And I just want to let everybody know that this is not just sort of a report out of end of work. It's really the beginning of work. So anybody interested in connecting with any of these teams, please continue to contact the PIs. They'll be very interested in talking to you. The next presentation is Ryan Gardner and Raman Arora. Ryan is going to be presenting risk-sensitive adversarial learning for autonomous systems. And also Then Nguyen Tang is going to be presenting offline reinforcement learning. Oh, so Ryan's on here?
Yeah, it's just me.
Hi everyone. My name is Tan. So I'm working with Raman Arora, and we're from Department of Computer Science, Writing School of Engineering. So today we will give a talk on our joint work on offline reinforcement learning accelerant in high-stack AI application. Before we go into the details about offline reinforcement learning, let me give a briefly overview about machine learning background. So as you all be aware of the recent empirical success and even technology breakthroughs in AI and machine learning recently. So you might wonder what makes modern machine learning really work so well in practice. And the two key components for modern machine learning is usually first, the big model, and second, the big data. So big model is usually a huge multi-layer neural networks. It can contain up to millions of parameters trained by stochastic neural networks, stochastic gradient descent, and usually trained on a large collection of data. So for example, in computer vision, we have like a collect image net. It contains like millions of label images. So that's very huge collections of label data we have in computer vision. So there's a huge difference between prediction in supervised learning and decision making in reinforcement learning. So in supervised learning, what we have is usually we have the data that's coming from the same distribution as the training data. So we call it IID data. And also in supervised learning, we have the graph through supervision. This means that every time we see the training sample, we also see the true labels of that sample. It tells us what is the categories of the image. For example, the image, the cat and dot, so it goes on with the labels of the cat and dot. The objective in supervised learning is to predict the right label given for example, the image. But in reinforcement learning, things is quite pretty fundamentally different. So in reinforcement learning, every decision we make at the time, it could change the future inputs in the future. And also, there's no supervision in reinforcement learning. So in reinforcement learning, we only given abstract goals of achieving some given task. For example, how to play some game, how to drive in the car, and then there's no supervision in that task, and the objective is to accomplish certain tasks. So reinforcement learning is basically the interactive learning loop that have two main components. The first is the agent, and second is the environment on the world. So the agent will iteratively interact with the environment to get. So the agent will, every time the agent interacts, will try to execute some sequence of actions, and at the result of that action, they will receive some kind of immediate rewards. And the goal here is to, after some time, the interaction is need to accomplish some certain tasks. So numerically, it needs to accomplish as higher rewards as possible. For example, in the example of the autonomous self-driving car, so we try to manipulate the car in the way that it can go to the target safely. So the question is, does the online reinforcement learning really work? And the answer is yes, but it only work in the case that the online interaction is feasible and plentiful. So we have several impressive empirical successes of online reinforcement learning in simulator environments, for example, in the AlphaGo and archery games and some robotic domains. But it's only when reinforcement learning is notorious for requiring a lot of samples to be able to learn a useful policy. And that's something unfortunate for safety assurance in AI, because in some high-stakes applications such as self-driving cars, financial investment, or clinical diagnosis, online interaction could be unethical and very dangerous. For example, in dynamical treatment regimes, what we want to do is we usually try to devise a treatment policy on real patients. And if we evaluate a treatment policy on real patients, that could be something very dangerous and unethical to do that interactively. So that's why comes the new approach of reinforcement learning, something called offline reinforcement learning. So what offline reinforcement learning do is that basically there's no online interaction with the environment. What it does is it's leverage whatever historical data it has. So for example, the past experiences has been collected before, and then no online interaction with the environment. And then the offline reinforcement approach will train a reinforcement learning algorithm on whatever offline data we have to extract a new policy or useful skill from the offline data and then use that learned policy in the real world. So the big advantages of offline reinforcement here is that no exploration with the data, with the environments, and also because it uses on the offline data, so it can leverage the huge amounts of available historical data it have in all the system. So I want to emphasize another application of the offline approach in the financial investment, for example. So usually people also recently also can build a reinforcement agent to learning to trade from some zero market. However, so online reinforcement usually requires a lot of sample. So by the time it learn a useful trading policy, it already incurs a lot of financial loss. So that's something unfortunate. So in offline reinforcement, they will leverage the historical trading data to extract the useful policy. So these are great things about offline reinforcement, but what are the challenges? The key challenge and the key fundamental problem in offline reinforcement is something we call distributional shifts, or it's counterfactual learning, because the data that have generated, the policy that have generated the offline data can be very different from the policy that we want to learn. So what if like the behavior or the skill from the offline data is not the one that we want to learn? We want to generalize the behavior based on what we see in the offline data. These are brief overviews of the offline reinforcement problem and the application in the assurance and safety. And here we would like to highlight some of our recent results on this space. So the first the first group we have is, so we mostly interested in the theoretical aspects of the offline reinforcement learning. And the recent role we have is we deal with offline reinforcement in the huge state space. So it's mean that in practice, the state is like high dimensional, it's very huge, and we need to make the generalization to the unseen states in the lost state space. So we use a deep neural network to train on that's offline data. And then we, in this work, we gave a polynomial time algorithm that basically it's based on like we perturbing the rewards in the offline data for several times. And then we train multiple deep neural networks on that perturbed data and using stochastic gradient descent. And then we proved that our methods can find the optimal policy using only polynomial number of samples without any uniform data coverage assumption. So basically it means that large-scale offline data is feasible and possible with the right technique. And the second result we have is like, basically like under the gap assumption, the assumption that when the optimal values of the optimal action is well separated from that of the suboptimal action, we can derive a computationally efficient algorithm that can improve the rates of convergence. So it can improve as much as from 1 over square root of k to 1 over k, where k number of samples. And that's pretty much what we have for the offline reinforcement link. Thank you.
Thank you very much. Okay, for the next presentation, it's going to be Dr. Alan Ewell, his team with Yin-Chi Chow, and Philippe Berliner in physical domain adversarial machine learning for visual object recognition.
Okay, thank you. Okay, we have a terrible title here, which I'm not responsible for. Far too long and complicated. So so this work is myself, Phil Berliner, and Yin-Chi Chow. And here's the basic background overview. So AI vision algorithms are known to be fairly susceptible to adversarial attacks, and somebody, I think it was Ralph Semmel, mentioned it earlier that companies are companies which try to make automated cars are going out of business because the algorithms don't really work in reality. Okay, now that's a big problem, and actually there's a bigger picture here than what I'm presenting, because I think a basic problem is when we test AI algorithms, particularly vision algorithms, we do not test them correctly. We need to test them in a far tougher manner, and I gave a talk at MIT just a week ago making that main point. Here, the issue is particularly that the attacks that people have used on AI algorithms that will cause them to fail have been in 2 dimensions, and so you may wonder whether these attacks are, will they happen in the real world? Frankly, for myself, I think, okay, even if they happen in 2 dimensions, that's bad. Why on earth did the algorithm make those mistakes? But still, there's the issue about them being in 3D. Now, an advantage of doing this acts in 3D, and there isn't time for me to discuss Yingxi's work, there's I think a poster about it, is that Yingxi and his group have managed to develop some rather nice attacks in 3D where you can cause a car to sort of follow the car ahead and do whatever the car ahead wants you to do, etc., with the, against the standard sort of type of AI vision algorithms. So since they're attacking in 3D, we need to defend in 3D. But in fact, I think we ought to be doing this anyway, because if you study human vision, which is one of my motivations, humans, when we recognize objects, we don't just say there's a car there. We say there's a car, here is the 3D orientation of the car, there is the boundaries, there are the parts of the cars. This is what we do anyway, and this is not yet what AI systems generally do. So a challenge here was to develop 3-dimensional models which would have these types of abilities, and also to defend against anything that Yingxi and his team will come up with. So the slides are a little bit sort of, well, not great, because this is all very recent work, some of it's about to be submitted in a week or so, is to say that we've now developed 3-dimensional generative neural net models for objects, which we could use as a sort of rather alternative to standard deep networks. And here I couldn't really believe this one myself. I'm not sure I do believe it, but here you're still able to recognize the car despite this enormous cat that's standing in front of it. Here it's also generalizing to this other car that is really rather different from the cars they're trained on. So having these 3-dimensional generative neural net models are, I think, hopefully a way forward here. They build on the 2-dimensional compositional models that we were using for the first part of the grant. The overview, and I see there's an embarrassing mistake, these are not neural mesh models, but these, and really the title ought to be analysis by synthesis. So this goes to an idea that came up in vision and other parts of AI, actually right from the beginning, 1950s, where you have models for generating data, and then to interpret the data, you just work out which model generated it. Seems a very nice conceptual idea, doesn't really work, or has not really worked well. The way we're managing to get it to work now is, and I hope somebody's keeping track on time here, is to have models that are generated on certain features, not just directly on the image, and there's a lot of technical stuff that took us a bit of time to work out, which is how you actually get these types of features, etc., relates to compositional learning and other types of methods. There's an obligatory math slide here, because I started life as a mathematician, but it's just to say there's mathematics here if you want it. It's not incredibly complicated. But the difference between this and the standard models is you're trying to build a model to generate the features in the image, not ones to just take them and classify them, which is what standard deep networks do. So we developed this, and originally we were doing it not for object classification because we thought that was too difficult. So we did it for human pose estimation. And particularly, we wanted it to work not just on the data it's trained on, but on out-of-distribution data that also came up in the previous talk. You want it to generalize outside the domain that it was trained on, because otherwise it probably won't work in reality. So here you could estimate the orientations of cars and other objects fairly reliably, despite large amounts of occlusion in them. Okay, the more exciting thing, which is shown just on this slide, though, because we haven't really fully written the paper yet, was to say, okay, well, estimating 3D orientation is fine, but really what you want is to classify objects as well. So for some time we found that a little bit difficult, and then we realized there was actually something obvious that we'd missed, which enabled us to do it, related to how we got the features. So now I think we can finally have these types of inverse rendering models that can recognize objects about as well as standard deep networks if you test them in the standard way, but which are far more robust if you test them more adversarially with occlusions and various other things like that. So you test them in far, more challenging ways, because that's more, a better sign that they'll work on the real world. So that's starting to work out. And also you can extend this as well. As I say, you don't just want to classify, you want to classify, you want to find the orientation, you want to find the boundaries, and we found able to find the boundaries reasonably now as a first step. We also want to find the parts, but we can't do that yet. So what we're doing is developing these 3D generative models of objects as an alternative to the sort of standard deep networks, because they have models of the underlying geometry of the objects, which helps. And they generalize the previous work we've done. And we've now got performance results saying that they're better for 3D pose estimation under challenging conditions. Also, I think better for object recognition under challenging conditions, and equivalent to deep nets when they're not. And as we develop them, they should be more robust to other types of attacks and anything that Yingxi and his group can throw at us. Okay, that's it. Thank you.
Any questions? Alan, to go from 2D to 3D, to what extent do you require structure, like to know that, well, it's a car, cars have 4 sides, they have a roof and so forth, or are there tricks that you can use to expand that domain of?
Yeah, I mean, we tell them that. We give them, you start up with CAD models, you can get those for almost nothing. You can, you can learn to interpolate and generalize from those. So I think you need to put that knowledge in. The standard deep nets don't have that knowledge. For myself, as a, interested in human vision, every infant older than 5, has that knowledge because they've played with these objects and they've got, they've developed that and they've learned all that structure for themselves. Deep networks don't have it because deep networks are trained in a machine learning based approach which doesn't allow them to have that knowledge. So we're really trying to put in the sort of knowledge that a human would have, because partially because, hey, facing it, human vision systems are far better than AI, and don't listen to anyone who doesn't agree with you there. I mean, generally, they're far more, human vision is far more robust, etc., able to generalize, and I think partly it's precisely because of the 3D models that they've got in there.
Thank you.
Yeah.
Yeah, so I'm just curious. It seems like there's a lot of those having to do with lighting models, size estimation, and I'm talking relative size estimation. Is it in the near field or is it in the far field? Are those being inferred by your system, or are those things that could become inputs to your system?
Well, size, we've got a certain amount that depends on the features we've got, and we are learning nice features which are invariant to certain things. They can't be invariant to a huge range of sizes. They can be invariant to certain ranges of sizes, and they can also be invariant to certain lighting conditions. I think these models as sort of starting points, because really, they're a way to get started. If you want to have a real generative model that can generate a realistic image, that's complicated, and then inverting it to go backwards is, extremely complex as well. If I'm recognizing a car, do I care if it's my car, your car, clean, dirty? I don't. So I don't care about those details. I want to get rid of them by putting them into features. But sometimes I may want that. So later on, one should have more realistic generative models that can generate those types of things. But to do inference on them, I think you may need to start off with these types of models that just don't care about that, give you a coarse estimation, which you can then refine by using more sophisticated models afterwards.
Thanks.
Yep.
Okay, thank you so much.
Okay. Okay, thank you.
Okay, the next talk is given by Dr. Takagusa, and he was one of the PIs with Jeffrey Michael, Josh Muller, and Jonathan Asani, and he's going to be talking about assured autonomous vehicle policy.
So how does the animation work? Or can
You should be able to click
I?
on
Okay, all right.
it. Are you this one, I think?
Yeah.
Yeah.
Can you make it full? Yeah, thanks. All right. So first, I want to acknowledge my team members. And what's important here is that we come from not only from the APL and from the Whiting School, but also the School of Public Health. And Todd Chang and Maddie Golob are in the table back there. They're going to be presenting the poster. Okay. I also want to acknowledge David Silverberg's help. He was sort of the intellectual, high-level intellectual guidance, because the project is kind of unusual. It's quite different from the ones that you've just seen. So what was our aim here? Really, it's policy-oriented. So that's why it's so different. Is that we're looking in the policy realm. And our goal is really to look at the way to gain public acceptance of AVs. So AVs, we know they're safe. They're going to be far safer than human drivers. But that doesn't mean that the public is going to accept them. So that was really our primary goal. And to kind of get to there, we have to work closely with our colleagues in School of Public Health, because they have a sense of what the public is like, how their perceptions are of autonomous vehicles. One of them sits in PAVE, that's the Partners for Automated Vehicle Education. So he sits with the industry, and so they have a sense of the public opinions. So what we did is we tried to influence the AV adoption in the public by showing how AVs can provide social benefits. And there's 3 things we did. We engaged with stakeholders, we did simulations, and used that with our stakeholders, and we also did a national survey. And for one of the stakeholder groups that we worked with, was in Cherry Hill, South Baltimore. You've probably never been there. It's south of Fort McHenry. It's not a particularly nice neighborhood, but of course there's residents there, and the city of Baltimore is trying to figure out how to really improve at least the mobility needs of that community. So this is one of the stakeholder groups that we worked with. This was just before the pandemic. But what's interesting in this group is that they came from many different sectors. So not only from the community itself, but also there were some transportation experts there. There are people from the Mass Transit Authority. So because if we're going to introduce mobility there, they want to see how they can work with us. So it was many stakeholders there, and then we tried to figure out, what the future, how can we make a future brighter for this community? And I guess some just very brief demographics there. There's a table there, but if you look on the left side, you can see that most residents there do not own a car. There is bus service there, but it's very infrequent. And there's if you want to get healthy food, you can't get it in that community. You have to go outside. If you want jobs, if you want access to jobs, it takes a very long time because of the bus services and so on. So there's this cycle that happens. For people, if you live there, it's very hard to get to employment. It's even hard to just go get an interview. So this access becomes a very serious impediment. And then what happens is that the tax base goes down, ridership goes down, and then the city says, well, but they don't need buses because hardly anyone rides them. They don't go to work. So it's a cycle here that needs to be broken. Right? Oops, sorry. Okay, so what we want to do here is this is just an approach of the overall project, is really to first run what is assuredness. So assuredness is more than at the individual level. It's more about the technology itself, but it's also a broader vision that should include the communities and larger groups. And that's because if you look at the perspective from the industry itself, the automotive industry, they know they are facing serious problems. They are fully aware of it, and that is because even if they develop the safest vehicles that you can imagine, and they're doing that now, the public is not ready to accept them riding around in their neighborhoods. They're just not ready. And I'll show you some survey results. Okay, so the simulations, of course, that's the engineering sort of toolbox, is that we can simulate what happens if we have these vehicles and deploy them in certain strategies. And then I'll talk about the survey. All right. Okay, so the simulation is not that complicated. We use something that's already been developed. It's called Sumo. Yeah, it's nothing to do with martial arts. It's a simulation of urban mobility. And but it was developed for automobile cars. It was developed for vehicles. And what we did here is we modified it because what we care is not about how fast can a car make it to downtown. That's not our goal. Our goal is how can it serve the people in the community. So we sort of repurposed this code, this commercial code, so that what we did is we added people to it. So it's sort of like, yeah, it's very fundamental to us, and it seems so obvious. But it's kind of funny that this kind of code that's used worldwide, they just care about cars. They don't care about the people. So here we actually have to include people in our models. We have to add code so that there are pedestrians there. And the pedestrians do actions that are different than cars. They go to bus stops, they ride the buses, and so on. So that's what that was sort of our contribution, technical contribution to the project. Okay, so now I had to see if this works. Do I click it here? How do I? Let me see. I'm trying to run this simulation. Is there a? Oh. Yes. Oh. Great. Thank you. Okay. So let me explain what this is. So this is a loop shuttle. I'm just going to show an AV loop shuttle. And you'll see these people walking around, the green and the red. The green are the ones who are going to go and look for the bus, and then they're going to hop on the bus and take it to the, oh, okay.
I'm just going to see if it works.
That's fine. Yeah, this is fine. Okay.
Oh. Okay. No, sorry. It's not working.
Oh, okay. It's all right. Thank you. Thank you, Veronica. So what happens is that they board the bus, and then they take the bus to the light rail station. The light rail station is not in the picture. It's a little bit outside. It's outside of the neighborhood. But here's where we were answering one of the concerns of one of the stakeholders, which was the MTA, the Mass Transit Authority, is that you can't just put in these vehicles and have them serve as a taxi service. You need to engage with the MTA, and of course we agree with it. So that was one of our scenarios that we developed for the stakeholder group. All right, so this is the most optimistic scenario, and it's where you have what we're doing is we're comparing the travel time to get to I think it's healthy foods. So this is on the left is a heat map showing The red means it takes a long time to get to the healthy food outlets, which is outside of the community. And one strategy is to use ride sharing. That's a little bit too aggressive. You require a lot of autonomous vehicles to deploy that strategy. But it's it has a very nice outcome. The time to get to the healthy foods is very low. In the poster, we have another scenario which is more realistic, where you have a shuttle. Okay. Then I can't explain every part of the project, but the other main part was the survey. And what we're trying to do is, first we're trying to get the baseline opinions. So what do people think about AVs if they're in your community? So it's this NIMBY part, that not in my backyard. Or if there's AVs, they're going to be in your streets. So that was the baseline question. Then we rephrased the question. And so we had survey experts to help us doing this, so that this is how they set up the survey. And you can see in the red, that's the added part there, is what if the AVs were used, in this case, for older adults. And we did different groups. You'll see that in a second. So what we're trying to do is to just state the initial question, but with a different viewpoint, which we hope would influence their opinions. Okay. So this was it was a professionally done survey. It was we researched on how to set it up, and they actually call it survey instruments. So it's an instrument, but you can think of it. It's a sensor. You're trying to measure public opinion. So it is a technical aspects in developing this survey. Anyway, so we got over 2,000 respondents around the nation. And here are the results here. So the top is the baseline, right? So this is, you ask flat out, what do you think of AVs in your streets? And you can see that more than half say are opposed. And that's not a surprise. That's not a surprise. The industry already knows that. And then, there's also some uncertainty. That's on the far right. Okay, and then you start putting in some scenarios. So there was the sentences I put in red. So one is, what if we use them, if the industry purposely uses them to, deploys a subset of their fleet towards helping older adults or low-income regions like Cherry Hill or vision impaired. And you can see here that when you add that, the opinions shifted quite dramatically, and that's what we want to see. So we show this to the industry, so that now we have to figure out if they are willing to, there's cost involved, of course, for each of those scenarios. But the benefit, of course, is that if you get better, wider acceptance, they can sell more cars, right? So that they need that market. So that market won't appear if we stay at that top. You have to get to these scenarios. The industry has to buy in, but the community benefits. So that's sort of what our survey indicates. I just want to put this into context of shared autonomy. So the level here, the idea here is that there's different ways to look at assuredness. It's more than just can the vehicle navigate without running over somebody. It's bigger than that. And I think Hopkins is really the ideal place to do that. I'm just going to go to my last slide. Hopkins is really the ideal place to do that because we're so good at collaborating. We're much better at collaborating than any other university in the U.S. There's no question on that. For instance, our collaboration between engineering and public health, and you should understand public health is not just medicine. It's much broader than that. And our school of public health here is the best in the world, so it's something that we should leverage. If we team up with them, usually engineers kind of shy away from policy. It's like, no, that's politics. We'll develop the technology, deliver it, and just see what they do. But that's not that. We don't believe that's how it should evolve, and certainly not with autonomous vehicles. The engineers should be involved in every step, from developing the technology to making sure that it becomes accepted, not only by individuals as driving the vehicles, but also the communities and the larger society. All right, so that's my talk. Yeah, thank you.
Any questions?
Jim?
Yeah, this is about public policy, and a big part of that is acceptance. It seems like there is a strong aspect of industrial engineering design that goes into that, and it's almost bolstered by that survey you showed, where there's a lot of opposition until you get the use case, and it'd be interesting for your thoughts on clearly marked vehicles and how public perception might change if they were marked for the blind, right? This is obviously an autonomous vehicle, and it's on the road to support vision impaired. Do you have any opinion on the role of industrial design or how things look since we're talking about public acceptance?
Yeah, I need to talk with you. Yeah, that's really good idea. So we are talking with the industry through PAVE, the organization, and I think we do need to bring in ideas. So the industrial engineering viewpoint, I think, would be valuable. Are you at Hopkins? Or?
I'm at APL.
Excuse me?
APL?
Oh, yeah, APL. Oh, yeah, that's Hopkins. Yeah, okay. So yeah, thank you. Yeah, I'd like to, catch up with you and get more thoughts on that. Thanks.
Sure.
Jim.
Well, that's a great question. I was going to ask about the business model side of it. So have you thought about, how can one incentivize the creation of these types of services? And I'm wondering, if they deliver these individuals to a shopping mall, for example, where they're doing shopping, is there an incentive for the shopping center to provide support for the trend? I mean, how do we actually make this work?
Yeah, very, very good. Thank you, Jim. So actually, in the local level, there were some of the stakeholders were owners of grocers, local grocers, and they were definitely for it. They think would be invaluable to. What happens is that they would have more customers demanding healthy foods, and then they would, there's a lot that happens in that scale. But we're also looking at the national scale. So that one is hard to sell, but this survey was very new. It's only been, we only did this a few months ago, and we're presenting it at the TRB, the Transportation Research Board, in January. But we're also trying to push the industry. So Jim, as you know, one of our team members, he has a lot of experience in government in NHTSA, and so he's going to go and reach out to his contacts. So it's through that we hope that we can turn around not only government but more the industry side. It's really the industry that has to buy in. But I think. The way it's going now, the market is not opening up to AVs. So I think they are really searching for solutions. So I think we believe they'll be receptive. Thanks.
When you're surveying the community that you want to deploy the autonomous vehicles in, how do you build trust with that community that they're not just being signed up to be guinea pigs? Also separate out the economic costs that they would face using autonomous vehicles as opposed to just increased bus service.
Oh yeah, that's a very good question about what's the best way to work with the community. So we did. There were community members in that group, and we're continuing to work with Baltimore City. Those are things. So it's not like unanimous. So when we have a stakeholder group, it's not like everyone agrees. So there is tension, and we have to resolve it. But that's part of good policy making. Is that you're always hitting on various stakeholders, domains, their boundaries, and you have to navigate that. So those are things. Those are not easy questions to answer, but my colleagues are very good at much better than me as an engineer in working through that, and it's through that we're going to be wrestling with the kind of questions you raise. So yeah, thank you for that.
So we're going to take a fast 5-minute break. Welcome back, everybody. So the second half, the last few presentations, going to be led off by Sarah Rigsby, who's been working with Matt Gubanich and Lexi Basantis on human-centered trust framework.
All right, thanks, David. Welcome back. It's always fun to go after break. I hope you've had a chance to get some sugar and caffeine. Post-lunch slump is always super fun. I got a thumbs up from the back, so I love that energy. Appreciate that. So as David said, I'm Sarah Rigsby. I work at the Applied Physics Lab. Myself, along with Matt and Lexi, are human-centered design strategists. And what we do is we focus on really the intersection of technology and humans across a wide range of projects and perspectives. And so what we're going to be sharing with you today is our trust framework that we developed from our work over the last couple years. All right, so as we've been talking about, autonomy is everywhere, right? And it's only becoming more and more integrated into our daily life, whether it's autonomous vehicles that's being tested and deployed in Baltimore City, could be autonomous trucks that's transporting goods across the country. We're seeing these sorts of systems become more and more prevalent, which means the stakes are higher and higher to get them right. And not just get them right, but to make sure that we're thinking about how do we get them right for everybody within society. So what goes into assurance? Right? It's a whole lot of stuff, right? How do we make sure that these systems are trustworthy and beneficial contributors to society? How do we make sure that we are able to test and evaluate them in these really complex, always changing worlds? For these algorithms that might not be as easily transparent or explainable to a human, how do we make sure that we really understand what they're doing day to day? So all of that and more goes into the broad topic of assured autonomy. And what myself and my team were most interested in really exploring was, what does a world of assured autonomy look like from that human perspective? So our process that we like to follow being human-centered designers is we really like to go do ethnographic research, and we like to do a lot of interviews and really sitting down and talking to the humans. And so what we did is we did a wide range of interviews with a really diverse set of stakeholders, a diverse set of viewpoints, both internal to the IAA as well as external to the IAA. And what we really wanted to probe was, how are people perceiving and understanding trusts? How do they think about ethical development of autonomous systems? How do they think about the impact of autonomous systems to both individuals and a variety of communities, like you just kind of saw in our last presentation? And so we learned a variety of things. And so the first thing that we really learned was that assurance is a relationship at its core. So different communities and different individuals, they all come from different backgrounds, and so how they perceive and how they approach these different technologies is going to be different both within themselves, but also different than how engineers and developers are going to view and engage with this technology. This is especially true if there's a difference or disparity between the education around AI and autonomous systems and when they should be used and when they might not want to be used. One of my favorite quotes is, assurance is never going to be accomplished by a researcher at a whiteboard, and I think that is really important, because what this talks to is exactly what Takagusa and his team were talking about before, where it's not just going to be one group of people that solves this. We really need to get that diverse group in the room. And really, large part of what I do is empathy-based, so really focusing on that empathy component of that relationship. We also learned that one thing that we want to think about is, how do we make sure that these systems that are being developed are safe or safe enough? How does that vary across these different communities and individuals? How do we think about the different groups that really kind of come into play with assurance? And so when we think about assurance, we think about it arising as a result of this kind of social relationship between the builders or the stewards of the technology and then the recipients or the users of the technology. So to explore that and unpack that a little bit more, if we have kind of an assurance at the middle, and we have recipients and stewards, and those are kind of the two groups that we're really thinking about, when we think of recipients, we really think about trust, right? And these are the users who may have anywhere from vast experience to no experience using these sorts of systems. And really what they're doing is they're putting their trust into the stewards or the builders of these systems to make sure that due diligence is being done, that these are not the people, the stewards are not, or sorry, the recipients are not the ones who are gonna know if it's safe or safe enough. That's really, they're putting the trust into the stewards. So there's a responsibility of these stewards really back to the recipients to make sure that due diligence is being done across the whole spectrum of the capability of the systems. And so diving into that a little bit more, when we think about trust, we also really like trust is a really tricky concept, right? So how people trust varies individually, and how you might trust a piece of technology could vary based off of your experience with different technology in the past. So if you've had a really positive experience, you are way more likely to lean in and inherently trust technology that you come across. Conversely, if you've had really negative experiences with technology, you're way more likely to be skeptical and need more either information or engagement with technology before you're willing to kind of trust and engage. And so trust is a human concept, right? Like it's, technology aren't moral agents, but we can interact with them as if they are, especially if they're more anthropomorphized and depending on how they look and how they're integrated into our daily life. And because different communities and different individuals are gonna have different trust perspectives, the needs are not universal for trust. So unpacking that a little bit more, when we're looking at the trust of the recipients, as I mentioned, the experience of those individuals is really gonna factor in to how much trust, inherent trust, they might be willing to place into the responsibility of stewards. However, as humans, we are social creatures, right? So we tend to make up communities, and each community is gonna have a different set of priorities. And depending on what the technology is and the application of it, the communities that impacts really should have a driving voice in how this technology is used and integrated into their own community, and that is a way to help drive and foster trust within the priority of these communities. And this really made us kind of realize that all humans influence technology. So people exist throughout the entire life cycle of technological systems. So it could be the designers, the engineers, the marketers, the builders, the people maintaining it. It's not just the builders that really matter. And I'm sure we've seen this, right? Where there's a big difference between how a system might be developed and how it might be envisioned from being used, and then how a human outside of that system might pick up and use that technology. There could be a really big disconnect between them. That can also really vary depending on the different cultures and the different perspectives. And what really also makes us think about, as Taco was saying, like, how are people thinking about policy and how is that policy being legislated, right? So policy is a human problem. It's not a technology problem. And if we can't just ignore it and hope that like someone else will think about policy. It's something that we need to think about as we kind of go along. And so when we look at the responsibility of the stewards, what most people think of are the capability of the systems, right? Is it safe? Is it reliable? What are the metrics? How often does it fail? Is it secure to and resistant to like cybersecurity attacks, for example? And that's really important. Getting the technology piece right is hard, but it's not the only thing that matters on the side of the stewards, because surrounding all of these systems are the institutions around it, right? And so these are the people or the institutions and organizations that are bringing this technology and integrating it into your life. They're bringing it into your homes, and really understanding what are the motivations and what are the credibility of those institutions will go a long way to driving the adoption and the fostering of trust along these technologies. And so that, in its entire holistic form, is the human-centered trust framework that myself and my team have been working on for the past couple years, and we are still developing into a variety of different instances. That's it. Thank you.
Any questions?
Kind of maybe broader than just community. Have you looked at, I think you kind of alluded to like culture, but thinking about culture as a mechanism for unexpected outcomes in technology use or you know, just, I guess, yeah, any sort of like autonomous platform use.
Yeah, it's a great point. My team has not specifically, we've been looking at kind of developing this overarching structure, but I think that is a really valid point, and we've seen that in instances, I think both in kind of the, say like general population, but also in the military domain, where different military branches and different groups within have their own sort of experiences and their own artifacts that they point and look to. And so that's something that as we're thinking about the systems that we're developing, really sitting down with the humans and really starting to learn and understand and create that mental model of like what is their world and what actually has meaning within that is really important, I think, for the developers and the designers to do as they're developing the systems.
Sarah, I just wanted to say that I'm really pleased with where this is and where it can go. I think the important thing is to get the word out, to get in there, because right now it's a cacophony of opinions and concepts, and it's really important for us to get this out. And perhaps it's almost like a standards problem. And so I think that's kind of, we're moving into that next phase.
Yeah, awesome. Kara has also been pushing me on that as well. So I love the double support.
So I'm kind of curious, if I were in a startup and I had some app that, had an AI component to it that I wanted to release, and let's say that I'm struggling with how far I have to get it along in order to actually release it. What kind of is, how would I think about it? How would I kind of work through the structure? I know there's and by the way, I'll just say that in my robotics world, we always say that one darn erases 9 attaboys. The failures are really expensive, right? So.
Yeah, absolutely.
These different words, by the way.
But I think it's true, right? Like how, like a personal example for me is like when Apple Maps first came out for the phone, I did not have a positive experience, and so I basically like shelved that for Google and have never kind of gone back. But what I would say, not necessarily specific just to this framework, but what I think you're really talking about is that human connection, the importance of really understanding like who is the user, what is this technology for, what problem is it actually solving, and really sitting down and making sure like, do we understand and have we empathized enough with the user and really understand like ethnographically what their world is like, but also have we really unpacked what challenge is it solving, and is it actually solving a challenge in their world versus I made you a thing and they're like, this is great. I don't actually need that in my life. So I think really taking the time up front to sit down and understand that end user perspective is key.
I think also, to me at least, it suggests how do you operationalize the framework?
Yeah, so we've been developing almost like a set of guiding questions for each each of these 4 components, and then how thinking about like how does this fit into a larger ecosystem that we still very much working on, but like if you were a researcher or a builder, what are the things that you should be asking yourself kind of along these different perspectives and along the pathway of building and design. So for example, I would not expect everyone to be a human-centered designer like off the bat. So what do I know and what tools can I bring to bear to offer people like, hey, have you thought about this and what about that? And here's ways that you can leverage a variety of tools kind of along the pathway. You're in line, so.
Yeah. Thank you very much. Great concept, great presentation. As the economy continues to grow and there continues to be more autonomous systems and in fact potentially even autonomous entities, robots, cars, things in the future, autonomous services will enable other autonomous services. Have you thought in this framework that the recipients might not always be people? Right? That one autonomous system may need to be engaging with another autonomous system, and there has to be some level of assurance between them.
That's really interesting. In this framework specifically, we focused on the human. I think it would be really interesting to look at that specific example and see where is the human on that loop If the human's not on the loop somewhere, that's probably for a different team to kind of tackle, but more than likely, at some point along that life cycle or lifeline, there's gonna be a human, and that's where I would really wanna dive into and understand, like, how do these two systems work together? Where, how do they handle their competing priorities? And what does that actually mean for the human wherever it might live within the system?
Just really quick, kind of in the vein of perspectives and alternatives you did. Did you see either through data you collected or just anecdotally any correlation between age and acceptance and trust?
So we did not do any kind of analysis in terms of age, and I think what you're kind of driving to is different generations might engage and have different trust levels with technology. So that's not something that we've looked at. I think with the amount of information that we have and how we kind of gathered it, it'd be hard to kind of tease that out, but I think there's a lot of information and studies out there that do look at that, and that should be kind of included and really kind of thought about with whatever that technology is that's being developed. Awesome. Thank you.
Okay, next up is Chengming Huang. He's working with Yijing Wang over at APL, socially aware robot navigation in human environments.
Wonderful. I think, is there a way to make it like, I think that's right. Is there a viewing mode?
I think that will work. It's fine. All right. Thanks. All right. It was such a delight to speak after work on human-centered design. So I don't really need to motivate why we need to care about people. So this is a joint work with wonderful colleagues at APL, Yijing, Kapil, and Coben. I think Coben is here. So if you have questions about details, we will be happy to answer offline. So I want to start with just to think about the problem that we're trying to address here is this idea of social awareness in the context of human-machine interaction. And if you think about human-human collaboration and human-human interaction, we're pretty savvy in terms of social intelligence. And if we want to have a future where machine play a role in our daily interactions, then they need to have some sort of levels of social intelligence that we might have. So I will talk about two projects specifically that highlighted social intelligence and why we should care about it in the context of human-machine interaction. So the first one is the context. So I just say this. It's essentially why we should care about social intelligence in the context of human-machine interaction. The first example I want to talk to you about is this idea of navigation and why social intelligence is important in the context of robot navigation. A little bit of motivation. The past 2 years, we have seen many more mobile robots are roaming on the road here in the United States, but also in Korea and in Japan. They just, part of this is motivated by pandemic. They start to, send mails in Japan through autonomous vehicles. And when you see these pictures, they are roaming in the human environments. They are not just roaming alone. So naturally, they should care about the social norms as people walk around in the environment. So the project we want to focus on, obviously, there are so many social norms that we follow as we move around in our established environments. But one thing that we want to focus on in this project is this idea of grouping. Right? People usually walk as a group in many social contexts, even in the work environment, and people maintain this kind of grouping very seriously, right? So here's one example where the group just keep maintaining even though they are passing through many different peoples and surroundings. Surprisingly, the part of work has not been looking at this about social grouping. Most work in this space treat humans as individual entity and essentially do not consider the social nature of people working together. Right, so this is state-of-the-art simulation that models human behavior in the environment, And you can see this, they're essentially just not considered as a group, just keep cutting through the groups of people. So what we did in the beginning is to build this simulator that simulate the grouping behavior when people walk. So we have this open source implementation out, PySocial Force. Be happy to share it more. It's already open source, so if you want to use it, be very welcome. So take that, we started to run a reinforcement learning algorithm to train social agents to be able to follow human styles of behaviors. The way we do it is fairly straightforward. Essentially, have a cost function to capture this grouping behavior. I believe it's, okay, it's not here. So this is still VR, treat people as an individual entity. We essentially capture that and put that into our optimization functions, and we train just running through this multiply in our simulators. Here's some simulation results. If it plays, or not. But if you just trust me, they will play offline. I can also show you offline if you want. But essentially, with this training, we are able to train a socially aware policy that the agents will not cut through the intended human groups. Here are some results. Missing highlights. So this is our group behavior. We show that with this group awareness, we are not sacrificing traditional performance in terms of collision, in terms of efficiency to reach the goal, but we also minimize the group cutting, group intersections. So that was a nice plus to have this social awareness building into the navigation policy without sacrificing traditional navigation performance. So with this simulation, we move on to try it out on the physical system. So everything I've talked so far is in simulation. We put that into this robot. Hopefully this will play. So this is done in APL. Well, I guess it's not. Oh, I see. Never mind. Well, essentially, this robotic dog will not cut through.
Okay. What should I do?
Maybe got. No, it's embedded. Maybe because it's Google presentation now. Maybe that's a reason.
I suppose APL is very secure.
Yeah. But it's okay. I will be around, so I have videos with me. I will show people. Essentially, we try a few different scenarios where we have different walking dynamics, different size of people walking. This one example will be walking directly toward the robot. Here's another example where we have multiple groups, and the robot still be able to recognize the multiple groups and not violating the social norms. So this work just published a week ago at IRAS, which is one of the biggest robotics conference. We talked about this and got really good feedback. Another thing that we have been, since we started to work on this project, one of the things that we learned is there's no standard way, surprisingly, to evaluate social awareness in navigation. So we did this survey paper on what's the common way people do it, and propose a few potential metrics for essentially try to standardize ways to evaluate social navigation as an effort to move this field more collectively together. So this is in the context of navigation. Most of you probably have heard of this. The second project I want to talk about is error detection. Might be new for some of you. So the idea here is machines are going to make mistakes, even though we have put a lot of efforts into modeling and whatnot. They are going to make mistakes, right? And in the context of human-machine interaction, this is not good, right? So one of the things that we should do is to detect error early, mitigate them, and try to repair. And this is highly related to the trust that I just talked about. So how do we think about error detection? Traditionally, when people do this, it's very task-driven. You need to have a good understanding of the task, and anything that violates our understanding of the task, it's an error. But if you think about robots and machines in our daily environment, they can be operating under so many different conditions. So it's really hard to have this comprehensive model of task or domain that can help us to identify errors. So what we did is to leverage human reactions. When something is wrong, people react socially. So we've been looking at this natural social reactions to mistake in the context of human-robot interaction. When robots make mistake, people react socially, even though it's non-human-like robot. Even though the task is non-social task, people still react socially. They laugh, they have these weird facial expressions. Even if the machine is just a speaker, like a smart speaker, people still react socially when the speaker makes a mistake. So it's pretty robust evidence that we have that people react socially. So what we did is say, what if we can take this into account to identify mistake? Can we just use natural multimodal social reaction from facial reactions, verbal response as an input to detect if something is off? So that's what we did. Well, this is not with the quality that I was expecting, but essentially we built a computational model that take facial expression, verbal responses as input, multimodal input, and build this a real-time classifier to make a classification like whether or not the current situation is off of the typical situation. So the paper is here. It's also published 1 week ago at IRAS. It's very exciting, and this is the line of work where I keep pursuing is having these social response-based methods to drive error detection allows flexibility that we usually do not have in traditional error detection framework. So with that, thank you so much. I'll be happy to take questions, and I can also answer questions offline.
Okay, thank you so much. Next is Dr. Paul Stankiewicz, working with Dr. Marin Kabalarov. He's going to be speaking about regression analysis for autonomy performance comparison. Let's see. Which one is it? It's 8. Oh, it should be up already? Oh, okay.
All right, yeah. So I'm Paul Stankiewicz. I'm a senior engineer at APL, and this talk will actually be a little bit broader in some of the general T&E tools that we've been working on over the past couple years. Really trying to tie it together by what our vision for an augmented continuous integration framework is for both developing and testing autonomy. So in this diagram here, you can see traditionally the blue area. This is the traditional CI pipeline where you're running automated unit types of tests to look for code quality types of issues. What we're looking to extend this is to the orange area where we're doing automated testing of more of the performance and behavior-based aspects of autonomy that just go beyond code quality issues. And so the two tools that kind of fit into this vision that we're working towards, I'll be going over, giving brief overviews of. The first is the RAP tool, which is designed to do adaptive scenario generation for simulation-based testing, essentially a way of finding edge cases and failure modes in the autonomy that you wouldn't have been able to pick out individually. And then the second tool that fits nicely into this is the some of the IAA research of performance-based regression testing of as we make updates to the system, how can we automatically identify when things might be getting worse when we didn't expect them to be. So starting out, just a brief overview of this top RAP tool. Like I mentioned, it's a tool meant to focus on simulation-based testing, but do so, take Monte Carlo in one step further by doing adaptive scenario generation, applying some unsupervised learning to really suss out failure modes, edge cases, performance boundaries, things like that. And so within this vein, any type of large-scale testing, there's two pieces that you have to identify that are shown on the left there. The first is the testing space of what test parameters do I want to throw at the system. So anything from obstacle positions, weather conditions, mission parameters, things like that. And then the other piece as the test engineer that you have to define is the performance criteria that you're going to be evaluating the system on. Unfortunately, with both of these pieces, you very quickly run into the curse of dimensionality, particularly with the realistic testing spaces that you would throw at an autonomy. And so a lot of the techniques that RAPT and some of these tools employ really are meant to apply some dimensionality reduction, do that adaptive scenario generation to mitigate that limitation of such a large testing space in the system. And specifically for the adaptive scenario generation, what we're doing, if you think of normal Monte Carlo, as opposed to just randomly generating 1,000 scenarios to test your system on, what we'll do here is more of an iterative process where we're generating a small number of scenarios to run through simulation, gathering those results and scoring the performance of the system in those. And the key to this is using those results. We're building up a predictive surrogate model that can then be used to predict where untested scenarios might indicate failure or an edge case or something of that nature. And so this is kind of illustrated just with 2D example surfaces on the right there. The top plot would be an example of a standard random global type of scenario generation or sampling scheme. The middle plot is the adaptive scenario generation that we're doing, where we want to balance fully exploring the testing space, but preferentially focus our efforts on gathering information in those problem areas or edge case regions, which would be the blue in this example. The last step to this kind of is then to also employ some unsupervised clustering techniques to further pull out manageable analysis chunks for the developers and engineers, particularly when you're not looking at 2D plots, but you're operating in testing spaces in the teens of dimensions. What's nice about all this, though, is that all of this is domain agnostic, so you can apply it to self-driving cars. We've applied it to UGVs, UAVs, you name it. It's a general testing process that you can use. So bringing this kind of back into the CI pipeline, that top part is what's producing the data sets, modeling the performance landscape. The second piece then is some of this IAA regression analysis of comparing our current performance of the system to previous performance. And so the technology gap that we're trying to solve with this piece of the research is as you're constantly developing your system and introducing software changes, how can we use some of these same techniques that you saw in RAPT or other machine learning techniques to draw out now where we might be getting worse in performance that we weren't necessarily expecting based on those software updates. So a very analogous form to traditional regression testing, but now it's not just code quality, it's performance or behavior-based regression testing. And that's kind of illustrated with this diagram here. So the red box there would be an example of a failure mode that we made some software changes and was fixed in version B on the right there. The gray region, however, is an example of a region that didn't have a problem in the original version, but those software changes induced that new failure mode in version B on the right there. And this is the type of stuff that we want to automatically identify and pull out. And I'll show an example of this actually on how we're applying it to, or how we have applied it almost as a case study in developing an autonomous surface vessel path planner. So for this case study, it'll look at a 3D testing space, so a simple testing space to explain in a presentation of how does our path planner perform when avoiding single vessel encounters. So varying the relative heading, speed, and lateral offset of an oncoming target ship, a bunch of different geometries. And then measuring the performance of our ASV in mission criteria, safety criteria, and criteria essentially of how well did it follow the rules of the road for marine surface craft, all of which then boil down into a final score. So, kind of highlighting this testing process from the first RAP perspective, what this slide is showing is a comparison of the type of results that something like adaptive scenario generation is producing versus a handcrafted test suite. And so that plot on the left there is a set of 73 different single vessel encounters that was handcrafted by subject matter experts in the maritime community, meant to be a comprehensive test suite of ASV testing. Each of those arrows is a different scenario. That's not one scenario on the left there. The right then is that 3D testing space, and those black dots are the black arrows translated into scatter plot form. And so what we can see is just qualitatively, there's these large failure regions that were completely missed by that comprehensive test set and pulled out by the analysis. Naturally, these were then the areas where software updates were made to try to improve the performance of the planner, namely, trying to fix overtaking situations by emphasizing avoidance away from the current location of the target ship. And the final slide in this case study is showing that when we made those software changes and the regression testing was applied, it was able to pull out these 3 new regression clusters where those software changes to fix performance from the previous slide now led to these new behaviors of deficient performance, where without getting into the details, you can see the after software update plot on the right, where we essentially now have a region of blue scenarios there that are near collisions, representing unsafe behaviors that were unexpectedly induced by those software updates. And so, this is all I have prepared. Really, both of these tools are meant to augment that testing pipeline. What we're building towards is so that something like this, every software push or every version of your system that you tag, this type of testing pipeline will automatically be run, and a report of these types of results are pushed back to the developers, to have better awareness into the state of your system. Yeah, so that's where I'll stop there, open it up for any questions. Which slide? Sorry. The color scale on the right here, that final score, is made up a combination of this mission scoring or safety and COLREGS compliance. So collisions are weighted very, very heavily. I wouldn't say there were any collisions in this data set, but some of those blue regions would represent standoff range violations or minimum CPA violations.
Thank you very much. Okay, we're at the penultimate presentation, Dr. Aurora Schmidt. will be speaking with representing her other co-PIs, Marin Kabalarov and Greg Hager, on values verified assured learning for unmanned embedded systems.
Sorry, Veronica.
All right, so I have the privilege of presenting on behalf of my team, that is co-led by Professor Marin Koblarov, and I was the APL lead for this project. But I just want to emphasize that this project really represented a huge team of collaborators. So we also had Professor Greg Hager helping us out, Yanni Kuskalas at APL, who has since moved on, but he was the kind of the formal methods lead of this research, and just an incredible number of people, including close colleague of Paul's, Galen, right? So this is actually a great privilege to present work that's on the behalf of so many gifted scientists all converging on one problem. And so I thank the IAA for allowing us to do that. So our motivations and challenges. Complex autonomous systems, they are increasing in complexity, as you well know, and a couple target applications that are motivating us are surgery, autonomous surgery, as well as robotic vehicle applications, both in the commercial and defense world. These applications have high stakes to them. They're safety critical. And so finding those edge cases like Paul was in his adaptive stress testing, it's incredibly important. How do we deal with them? How do we find them? And how do we develop approaches to design safety verified perception and control techniques? So that was the overall motivation to this project. And so we came up with a multi-pronged approach that involved a lot of disciplines coming together and adding different types of technology to this architecture diagram. I know it's overwhelming. We tried to split it up into 5 different task areas, and you can see how they're fitting in to this architecture. Basically, our primary controller system is physics-based, and it's kind of using robust control techniques and logical-based models. This is actually architected with a simplex model or a fallback control model, where we also have a safety-verified fallback control system that uses formal methods to try and provide guarantees about the operation of the primary controller, potentially cutting off the primary controller if there is a envisioned safety issue. So task 3 focused on learning better models to capture the uncertainty in the perception systems of a robotic system. And that's very important because we know that perception is not perfect. Even with deep learning, there's still uncertainty there. So Kapil actually spearheaded that effort to try and estimate the uncertainties in these perception systems. Task 4 is much like Paul's task. Galen was leading efforts for adaptive scenario stress testing. So how do we simulate scenarios that will reveal the holes and the edge cases in our system? And then finally, task 5, which I think was really important to this project, was actually realizing this in a physical platform, a ground vehicle, which I have a picture of on the next slide. So, that's a lot louder. How do I mute it? So I'm gonna pause it because that's really loud. But basically, you can see our robotic vehicle that Marin and his students engineered. It's got dual GPS receivers. It's got, a very nice camera LiDAR system. And it was actually driving around Johns Hopkins campus, collecting, great experiences and not threatening anyone because it's really small, right? So anyway, that was really great to realize all of this technology in this example platform and test it out with real people and real situations and have it learn how to navigate Johns Hopkins campus. sorry, I would love to play the video, but it's very loud, and it's really just, you can predict what it is. So task 1 used the probably approximately correct robust policy search approach, and you can see it's kind of using tube-based guarantees for navigation. And if you want to know more about that, I suggest you talk more with Marin, as that's what his students were publishing on. Task 2, which I eventually led, was designing the fallback controller for collision avoidance. And we were originally conceptualizing this in the context of multiple vehicles on the highway, but we ended up testing it for this project for pedestrian avoidance. So we've got some models here that show anticipatory braking, where we're basically trying to use safety predicates that have been formally verified for aircraft situations and repurposing them for two-dimensional ground vehicle situations. And in the second merging example, we're trying to do a more complex maneuver that allows safe merging with moving traffic. So we have a publication that is about how we synthesize a provably safe controller based on these safety predicates that we had laying around from another project. And so I'd point you to that for more information. And then task 3, the pedestrian state uncertainty estimation. My best description of this is fancy deep learning with Kalman filters. So it brings together lots of great stuff. Kapil got an ICRA publication out of this, and it's actually a really important area of being able to understand what the range of positions that a detected pedestrian could actually be at, because having that characterization of that uncertainty is so fundamental to us being able to avoid that pedestrian. So that was a pretty critical piece of work. And then finally, never forget the stress testing. And we were surprised, at how many. So we wanted to demonstrate the value of a safety fallback controller, right? We didn't use the props controller, we just used a greedy controller, but I have to say, greedy controllers do well 99% of the time, right? So we were utterly surprised when our test engineer, Liz Dietrich, found thousands of examples of simulated collisions in the car lift framework. We didn't think it was possible. Basically, this car's maneuvering to avoid the pedestrian, and due to some weird bug, veers into the pedestrian right when it's almost about to pass them. It just really puzzling, honestly. And there's a lot of geometries that are of the similar nature that when what you need to do is sample pedestrians that start off really close to the vehicle in a way that maybe wouldn't normally naturally happen, but they're far enough away that the vehicle can avoid them, and just see what happens, right? So these scenarios ended up being really great for demonstrating the value of the safety fallback controller, which honestly wouldn't get used 99% of the time. But in these particular stressing scenarios, not a single one of them involve a collision with a pedestrian. So that's kind of the power of having formal guarantees, assuming that all the assumptions behind those guarantees are satisfied. So we had some great results from simulation stress testing, and lastly, we had really nice on-campus real-world testing that Marin's postdocs and grad students were coordinating regularly. We were doing, GitLab updates to the software, unrolling it on the vehicle, testing it out, collecting ROS bags. It was really just an amazing effort to get real data and really realize some of these concepts. So you can see actually there's uncertainty ellipses around detected objects and pedestrians on the right, where you can kind of debug what the tracking systems are doing. And you can see the first person perspective of the vehicle as it drives around. And so, yeah, I guess just to conclude, we got some publications, very appreciative of the support. And we're actually actively working to try to transition some of these technologies in ground vehicle systems for the Army and undersea applications for the Navy. And we'd love to hear more about what the next steps for IAA will be. Thanks. sorry, I got questions. Yes.
So I have one question. So you said the failures that you actually found in Carla were when somebody was there in a way that might not be realistic or was very close to the vehicle. But could that also be simulated by the sensor just didn't pick up that person until very late?
Absolutely, and the real sensor, by the way, was not a 360 sensor. So this could naturally happen by somebody just walking into the field of view, but having to come in at that angle. I was surprised, honestly. I don't engineer robots, so I would have thought we'd want a 360 sensor. But yeah, no, somebody could absolutely, like a little kid could run alongside the robot and then veer into it if they wanted. I think we might even have footage of that. Yeah.
Yeah, I mean, that sounds like the Uber instance, right? You know, you're at night, you only see what's in the lights in front of you, the person comes off and walks in front of you, so.
Yeah, so this really does happen. It's not frequent, but you want to be ready for it. Yep. Yep.
So from the simulation, it looked like you're just focused on maneuvering, and a lot of literature that continues to work on the problem of obstacle avoidance, whether it's pedestrians or at sea, focuses just on maneuvers. But what I've noticed is in the maneuvering logic, no one seems to incorporate slowing down.
Oh no, actually, our safety fallback controller only did speed regulation. So that was an interesting integration choice that we made. We thought about a bunch of different choices. Like one version is we could completely take control from the primary controller and choose a maneuver like you're saying. But what we did was just inserted velocity regulation into the primary controller. And so there were some interesting details to think about so that the guarantees would still hold. Like you had to consider all possible primary controller maneuvers. But basically the emphasis of this work was on speed regulation, actually.
Did
Yep.
you also look at the possibility of speeding up?
Yes. But I think the target vehicle speed was on the higher side because, Marin's all about performance, right? So he wants to get from point A to point B, effectively. So I think is probably not super feasible to speed the vehicle up too much from what the target velocity was.
There are certainly times where you want to go a little faster than whatever's coming at you will miss you. So.
Right. Yeah, but there is, so if somebody is crossing, you can absolutely go a little bit faster to get there first. That is an option, yeah.
Thank you very much.
Sure, thanks.
And last but not least, both Drs. Anna Buchuk and Mark Dresdy are going to be speaking about identifying factors to explain the behavior of deep learning systems. Very timely and difficult problem. Let's see. Oh, it's already open? Oh. Oh, there we go. Okay, good. Yay. Okay, I know it's somewhere here. Comments.
This doesn't work.
Oh, there.
They think everything's a touch screen.
There we go. Okay, good. Thanks.
It works. It's delayed.
It works. Okay. So Mark and I, we will be talking about explainable forecasts of disruptive events using recurrent neural networks. So probably for this community, it's not necessary to say it, but anyway, you know that the modern AI systems, they are very complex. They learn great, deep neural nets or others. They learn from inputs to outputs, but nobody understands why they're making the decisions they're making. And in many applications, it's okay. But there are applications in which it is not okay. And actually, one of the previous presenters was talking about autonomous vehicles and, will people accept them, and so on. And for example, there was this Uber self-driving car at the time, in 2018, famous accident in Tempe, Arizona, and people started, freaking out. The same is true for medical professionals. Same is true. I am from AMDS. We do a lot of things for missiles and other military. Definitely a neural network without explanations is not the way to go. So here what we are showing are, we are mainly showing the methods we developed for the application, which is called Crystal Cube. This was a project on which we both worked in the past, and it was predicting disruptive events in the future. Usually political events such as an overthrow of a dictator or some other bad political events. So over there we started by saying what is regular and what is an irregular event, and we were interested in predicting all the irregular ones. So regular was like, President Obama, term limits, so of course next president is coming, slightly more irregular descent point to like the UK Prime Minister David Cameron, when there was this was the Brexit vote, so he resigned and so on, and higher, and finally the catastrophic one, like President Mugabe, where there was a coup in Zimbabwe. So the ones on the right, not at the zero level, but higher, were the ones we wanted to predict. What we developed is a system in which we have GDELT data, global database of events, language, and tone. We have some word development indicators. We developed deep belief networks for autoencoding, convolutional neural networks for autoencoding. We had over 1,000 inputs to our recurrent neural nets, and on the right we are predicting those disruptive events. But after predicting them, and this is how this IAA project started, we wanted some additive, explanations. One of the methods was SHAP, so Shapley additive explanations. It is based on concepts from cooperative game theory, and basically it tells you which one of the variables are the most important one for a given prediction, and it divides them into positive contributions. So they are shown in red, so this is the ones which increase the output of the network, and the negative contributions that decrease the output of the network. So, okay, I'm going to skip certain things because we have only 10 minutes. Our forecasting results were good, not perfect. You will never predict with perfect accuracy events. We have a live website, and I was just texting somebody on the team, and apparently it is working. Sometimes the computer over there is down, and on that website you can see for every month we are making predictions. Usually it takes us 3 to 4 days for the method to collect the data, compute the predictions, compute the explanations. So right now on that website you should see still October predictions, but in 2 or 3 days there will be November predictions. So we show countries in different colors depending on if we are predicting that there will be some irregular event. Okay, this is an example of an individual explanations. These are SHAB values for some forecast for Yemen, in this case for January 2015. And this is actually the date in January of that year. There was an ILC, and President Hadi resigned after an armed militia seized the presidential compound. And you see in red those, I cannot read from the small screen, so you see like the inputs like accede to demands for change in leadership and so on. They have a high positive value. These are the most, the ones that are changed the forecast the most. Some accede to requests or demands for political reform and so on. And we have also some negative contribution. So this is an individual combination. The next one we did the same for all true positives, all true negatives, false positive and negatives, and these are scatter plots, and basically for a given feature, the SHAB value of the feature is plotted for each of the here true positive forecasts, and SHAB value is colored by the original value of the feature. Blue for low values, red for high values. And we'll be moving to Mark, but basically we have developed this method, and right now we are still working on getting some, we want to get some rules from the network. So not only to tell which variables, but also rules if A and B's and, an ILC.
Thanks. Okay, so, you guys, does this work?
The other one, please.
No, what's mine? But I don't like standing in one place. Is this? But they're looking at the board, so that's a good sign. There's a button. No light came on. Oh, now there's a light. Okay. My phone doesn't have a wire. I don't want to have a wire on my microphone. My laptop doesn't have a wire. So Anna talked about some of the challenges of generating explanations for these really complicated systems. And Crystal Cube is one of the reasons we picked it. It's a great example where no one is going to do anything unless, based on the prediction system, unless they understand why. Like the US military isn't going to deploy soldiers based on a perceived event because we said there was a 95% confidence. They need to understand why. So there's another aspect that we want to address in explanations, which is this tension between faithful explanations and plausible explanations. So faithful explanations is, this is why the system actually said what it said, right? Crystal Cube, as Anna said, 1,000 inputs. This is why it predicted a leadership change. The problem there is those are not always plausible. So that's not the way you and I think, right? This very complicated system is going to differ from the way you and I might actually process information. So there's a tension because we want to give people information in a way that they understand it, but we want to be, which is plausibility, but we want to be faithful to what's actually going on in the system. And this is a challenging trade-off. And so we want an approach that could address this trade-off. And so we had this idea of distillation through a proxy model, that let's take this really complicated system that's really accurate, like Crystal Cube, and then just build like a really simple model, like a user-friendly model that isn't trying to solve the task, but is just trying to mimic what the big model is doing. And the reason we like that is because we get a knob. The more complex our model, the more faithful it's going to be to the Crystal Cube system. The simpler our model, the more plausible those explanations are going to be because they're simpler explanations that people can understand. And now, by controlling model complexity, we have this nice knob we can tune to say, well, do you want more faithful explanations or do you want more plausible explanations? So the nice thing is this is a general approach. We've used this on Crystal Cube, but we also used it in other settings. So we used it for a medical prediction task. So here we are trying to predict medical codes. And what we found is that the distilled models, these proxies, were actually really faithful to the system we were trying to mimic, in this case, a convolutional net, but they actually gave us really plausible explanations as measured by doctors, right? So they were mimicking what the complicated system did, but they were giving explanations that we can more readily understand. These are some results run on CrystalCube, and we see the same results here, but another advantage of the system is that it produces global explanations. And what I mean by that is they're producing explanations that aren't true of just this one prediction, but are going to be consistent in the way the model thinks across many predictions. And so we end up getting predictions that are accurate, globally coherent, and actually much, much faster than other methods that are out there. So I just want to wrap up by saying a little bit of looking ahead, some of the things that we're thinking about. And one of them is thinking, what is the kind of decision that we want to enable? So take CrystalCube. What does it look like when a decision maker goes to this website, sees that there's going to be an ILC or some kind of other event, and then have to take an action? And one of the things we realize is that there should probably be some kind of interaction. There should be a way where the system can say, or a user can say, well, what's going on here? The system can offer explanations, whether that's of the kind I just showed or what Anna was showing, but then the user can say, well, tell me more, right? So an interaction like this, right? A user might say, this is a medical case. For women, and this is not my example, I should say. For women predicted high risk for lung cancer that are older than 65, why did the model decide to predict them at high risk? And the system actually offers an explanation. I'm not going to go through it. But then the user says, wow, it's surprising that whether the person lives in a city is so important, which is a nice way of saying, what's going on there, right? Like, tell me more. And the system understands that and can actually say, oh, yeah, let me explain that. And it helps the person build a better confidence in the system. This is not a real system. This is an example of what we'd like to enable in the future. And so this is one of the things we're thinking about now of what would natural language explanations look like. So we're happy to take questions. We'll be at the poster session. Thank you for your time.
Any questions?
Oh, yeah. Hi.
Hey, Mark.
Hi, how you doing?
Good.
Good to see you. Yeah.
Are you familiar with that work? I think there might be a good connection, or at least to see how this domain would apply to that body of work.
Yeah, so I really like what Cynthia is doing. So I'll make a kind of a meta comment. So I think if I can summarize, her fundamental belief is that really complicated systems are a contradiction to explainability. And we shouldn't be thinking about building really complicated systems. We should be thinking about building interpretable and explainable systems. And that might limit the accuracy, maybe not, like as the case you said, but it might limit the accuracy of what we can do, but what we will be able to do will be more useful. So I think, like, if I could, my base response to that is, I think it is true that if you can build systems that are interpretable, they will be more usable. I'm 100% behind that. I think, though, there is a limit to the types of problems you can solve using those systems. And we have to recognize that something like this is really complicated and is probably not solvable with a simple system. And so either we don't do things like this, I'm talking about CrystalCube, for example, either we don't do things like this, or we figure out a way to make those explainable. So yes, if we can build simple systems to solve our problems, they will be more explainable, that's great, and we might want to sacrifice some model performance to enable that. But I think there's a limit to the problems we're going to be able to solve using that approach. And it's unfair because she's not here to tell me why I'm wrong.
A corollary I picked up from her work, perhaps, is that you can use her method to determine if that's in fact the case. If your domain is beyond the limit of what could be turned into an easily interpretable system.
Yeah. We need to do more of that. There's too many people who show up with power tools when you just need a nail clipper. I don't know if those were right. I don't know tools very well. Do you use them for the same thing? Okay. But I think like that absolutely is the case. I mean, I see this with students who build this super fancy system, and I'm like, well, I could have solved that in like a couple lines. That's why we like, Anna, she gets credit for this problem. Like, she picked something super hard that I didn't think we could do, and then she proved me wrong, because it's really complicated. It's worth trying to do these really complicated things.
It's kind of complementary because you have either your system is easily interpretable or you have a system that needs your methodology.
Yeah, I think both are worthy of study because there are problems we can solve using her approach. I just think not everything will follow that.
Crystal Cube, what we developed, we can explain part of what it does using fuzzy ifs and rules. But not all rules are always true. There are always exceptions. So it is like sometimes you cannot put one rule, but you would have to put 3 or 5 just to explain, which makes it more complicated.
Explain that to my banker, by the way. They think
Are we allowed to keep going? Mark, well, first, both of you, this is really fascinating. One of the things I often deal with these learning systems with is like medical image segmentation. And there, one of the things you really would like is a custom version of confidence, or the ability of the system to explain how what it's seeing here right now, how similar it is to other things that it's trained on as part of the explanation or whatever, or an explanation that says, hey, this is really different than anything I've seen, but here's what was closest. How do those considerations map into what you're doing?
Do you want to go first? Okay. So again, I'm going to make a very big comment and then tie it down. So I think work and explanations is fairly new the past couple of years. I think it's very much limited by our imagination of what's possible. And unfortunately, I think what we can imagine as possible is not often useful, right? So you're giving me cases, and this is really true in medicine. So you're giving me cases where here's what would be useful to someone, like comparison to other examples and such. And I think being creative in terms of the types of explanations that we can give, right? So like in vision, a really common thing is you highlight parts of the image that are relevant, right? Like there's a lot of work on attention and masking and line that say like, well, these are the parts of the image that are most relevant to the decision. And often those are not really understandable to a person. So trying to push this into a place where, saying like, well, here are the previous things I've seen that are most useful, and trying to speak in a way where people can actually understand and incorporate it into their decision process. And that's one of the reasons I really like the rules, because it's taking SHAP values, which aren't always really understandable, and trying to push them more to ways that people normally talk. I think we need to do a better job of understanding how people make decisions and what are the missing pieces of information they need to make those decisions.
One historical note, explanations from AI systems is actually one of the very oldest things. You look at Ted Shortlett's
Yeah.
thesis, the main point of that thesis was the explanation mechanism in it. So it's a minor point.
No. So AI used to be dominated by knowledge systems, and then we discovered math. So we threw them away. Obviously, I'm simplifying a little bit, right? But we threw away a lot of that, and we threw away how to do that. And now we're discovering that maybe we need it. Yeah, it turns out that we need some of that stuff. But I wasn't doing any of this stuff in the 70s. So I wasn't working on this in the 70s. So I know, but I'm saying I have, my historical knowledge is incomplete. Yeah.
Any other questions? Thank you very much.
Thank you.
Marvelous job. I also just want to acknowledge there are two programs that were not represented here because they were not able to make it. One was Tamim Sukor and Yair Amir, Radix, which is runtime assurance of distributed intelligent control systems, black box, white box, optimization of traffic, and energy control. The other one is privacy and fairness, and that's Phil Berlina and Yinchi Chow. Number one, just how to ensure fairness, where you have underrepresented populations in medical applications. And number two, privacy, how do you kind of dial up and down your privacy to get optimal results? Anyway, if you have questions about those, I can direct you to them. And thank you for this section.